Hello everyone and welcome to this video about how to prepare your project for machine learning. And this is just a primer on how you should be thinking about machine learning approaches when you have some project that you in the future might want to apply it to. Because I get asked a lot like how do I prepare my data for machine learning and what should I be thinking about because I'm redesigning my system right now, or we have this new product that we are about to start up, and how should I be thinking about how data is stored and so on. So the reason why you want to watch this is, as I said, you have some new products that are coming in, and you want to make it possible to in the future apply machine learning, shortened by ML in this presentation. Or maybe you want to save some time when you in the future know that you're going to apply some machine learning. Or maybe you just want to make it easy to apply it in the future. So you can see you have three different levers here. You want to make it possible, you want to save time, or you want to make it really easy. And you might have some existing projects that you're thinking about how can we refactor our systems so that we can apply machine learning. And like, is there anything else that we can change in our system, how the data is stored to speed it up? Or are we actually already sitting on a gold mine in terms of resources of data and images and so on? So here is also three levels that I've identified that I see a lot of people are wondering about. So this presentation about getting an overview of the taxonomy of machine learning. So maybe you don't know the terminology. You hear all these buzzwords all the time. It's like, but what is this and what is that? And you don't know that. So then this presentation is going to be great for you. Or maybe you want to know what it means for your team to start preparing yourself in terms of time and cost and experience and resources and so on. Like what do you need to prepare yourself for in this future? Because machine learning is here to stay, and like how can we be a part of this future? Or maybe you just want to get a better understanding what this actually is. So maybe there is application for you. So if you're watching this and you are a developer or a mathematician, you will probably experience that this is a bit hand wavy at times. And the abstraction level here, I try to keep it fairly abstract, and I will also leave some parts out in total that, if you're implementing it might be important, but like in the terms of this presentation, it's not really important. And if you are a project manager or more non-developer people, you will probably see that there's a lot of name dropping going on with key terms. And I will highlight this in bold. And I still do this name dropping so that you will be able to speak with the developers in the same kind of language, non-ubiquitous. And also that you will learn this terminology. And if something is mentioned here and you're just like, what is this? Then you have to Google it if it is not explained, basically. And you will probably experience the quite opposite, whether you feel that the abstraction level is fairly low with many details. So you will be somewhere along these scales between these two. So let's start with the real basic questions like what is machine learning? And what it is simply a statistical representation of the data that it is trained on. So let that sink in for a moment, because that is basically only what it is. So you have some data, and then you train a model on that data, and now this model have figured out how to hopefully statistically represent that data, so that if you give it an examples that it hasn't seen before, it'll apply this statistical representation of the data that it has seen and make a hypothesis of that question that you're trying to ask it. So that is what it is. So it won't magically figure stuff out for you, but instead what it'll do is take some highly complex rules and figure them out by seeing a lot of examples. So how should you be saving the data? So it kind of depends on what questions that you want to ask it, as I mentioned before. So if you want to ask it a particular set of questions, you might need to save the data differently, or at least work with the data differently. And so what that means is that if you're gonna answer this question, you need to know at least the three most common architectures that we have in supervised learning, which is a keyword. And these are probably regression, classification, and sequence, predicting sequences. So this is what is going to be covered pretty abstractly in the coming slides. So let's start with this supervised learning that I mentioned. So what is that actually? Well, the supervised learning means that you have a data set, and in this data set you also have the right answers. So that if the model makes a hypothesis, it can be corrected against these right examples. And it does that until either the hypothesis is close enough to the real deal, or you run out of data, which is the most common case. And the correct terminology for this, like right answer, is this is called a label. And all the other variables that you have in your data set that you give as input to the prediction, these are called features. So in this example, you have like age, name, and device, and you have a column also called money spent. So here, these are the features. You give it the age, the name, and the device, and it's gonna try and predict how much money this user here is gonna spend. And so what it's gonna do is gonna make a hypothesis from the input features. You're gonna take that hypothesis and compare it to the actual real deal here, called a label, and it's gonna see how far off it was. And then it's going to correct it, and then it's going to try again on the next example. So here we have already made some assumptions from the data. That the problem we're trying to solve is to predict how far off the label, the money spent label, the prediction is. So this is called a regression, and I'm going to cover what regression means more in detail in the coming slides. So this is a very common way of how you would represent a neural network. And I'm going to refer to this as the models. Whenever I use the word model, you can have this image in your mind. So here you can see we have different layers, and they're stacked together here with arrows. And the data, you can't really see it, but the arrows are pointing forwards like this, from the left to right. So in the first layer, in the input layer, we're going to take the features that we have. We have age, name, and device. We're going to input these features, and with some value. And for each hidden layer here, for each unit, you can see that they're fully connected. This is connected to, every node is connected to every other node in the next layer. It's gonna send the data to the next layer, where it's gonna be multiplied with a weight, decimal weight that is stored differently in all these nodes here. So each of these nodes, they have a separate floating point number that it's going to multiply the input with. And then it's going to apply something called an activation function, which I'm not going to cover, which will modify the value a little bit. And then it's going to send it to the next value, and it's going to do that through any number of layers. And the number of layers doesn't really matter at this point. But you do that through some layers, and then you eventually get to the last layer, and now the value has been modified. All of these nodes here, they have a different interpretation of the value. And in the last layer, you're gonna send it through the layers, multiply it, and then you're gonna get one output here. In this case, we have one label, so it means one output. And that output is gonna be our prediction, how much money spent was spent. And now we're gonna take the real label, you're gonna correct the hypothesis against the label and see how far off were we. And then you're going to do something called the backpropagation, where you go backwards through the layer and you adjust all the weights on all the nodes here. And then you're back at the beginning. Then you take the next example, and now in the next example you're probably going to be a little bit less off. Basically, you're going to be a little bit more correct in the next hypothesis, hopefully, if you're doing it right. So it's going to do that for all the examples and trying to get as close to the real label that we have stored as possible. So that is regression. So if you instead think of something that is where the label is actually not a real number that we can calculate how far off we were. So in this example, we have a different data set. We have 4 input features. We have age, name, device, and money spent. So money spent here is not a label anymore. It's a feature that we use as input. So here we input all our features in the input layer. And in the output layer, instead what we have a label called pet. So we're going to predict what pet these users have. So it's going to be a cat, dog, lizard, or a hamster. And what's going to happen here instead, since this is a classification, is that all of these hypotheses here, instead of having a real number here, you're going to have a decimal number of the certainty of how far off with the prediction it thinks, how certain it is that this is actually the case. And in this particular example, you can only have one pet. So what that means is that maybe it's like 20% sure that it's going to be a hamster, 20% sure that it's going to be, you know, a lizard, 20% sure that it's going to be a cat, and then maybe 60% sure that it's going to be a dog. So okay, now dog has the highest certainty, and the prediction for our classification is going to output dog, right? Because it's going to think it's a dog. And then it's going to instead take a vector where it's the label is going to be 100% on pet, 100% on dog, and 0% on cat, lizard, and hamster. It's going to use that to calculate how far off it was, do back propagation as before, and then try for the next row. So this might be a bit heavy to understand, right? But what I want you to focus on here is the difference between how we have, in the regression example, we have a different output layer where we can actually calculate how far off it was from a real decimal value. And in this example, we can only say that we were 60% sure that it was a dog, and it actually was a dog, right? So we should have been 100% sure of that, and now that is what we're going to use. That 40% uncertainty difference is what we're going to use to correct our network. And also, like, you can have multiple outputs. You don't have to have one output. You can have multiple outputs. So that is the difference between regression and classification. And the third option that we're going to cover here is predicting sequences. And these are commonly referred to as RNNs, or recurrent neural networks. And if we step back a little bit here, they're going to look kind of like the same. They're also going to have like layers and stuff. But in this particular example, you can see that the weights or the predictions are propagating forwards through the network like this when we're doing the prediction. And the difference with RNNs is that they don't only propagate forwards, they can also, you know, propagate back to themselves an arbitrarily amount of times, and then eventually go to the next layer, propagate a little bit there, and then so on. And technically, these, I mean, like implementation wise, this means that you can predict sequences, and that's all you have to think about now. And if you take this is a node here illustrated, so you can see that it also has an arrow to itself at time t, and you can take this loop that happens, you can unroll it into time sequences like this. This is mostly for the developers and the people that are interested in this. You can unroll it like this, and you can see how it is actually the same thing, but like this, but it's just like unrolled. So it's the same thing, but it can also point to itself. And these sequence predictions, these are commonly used with something called a LSTM, or long short term memory. And the problem that LSTMs solve is, for example, if you have, it's mostly used with text. So if you have something like this, I am French, therefore I speak French, right? And intuitively, we know that it's going to be French here because, you know, you mentioned that you are French here. So then it means that you speak the language of French, right? But that might seem really trivial to us, but a neural network like this doesn't realize that that word is actually important, and it's going to be important later on. So LSTM solves that problem to identify keywords and later being able to improve the sequence. So maybe you have an example to make it more concrete, like what would you use this for? So let's say that you have a data set that looks like this. You have a set of events, and these events, the question that you want to ask, that you want to have answered with this is like, you have this set of events, right? You can sort them in the time that they happened for each user. So the question you want to ask here is, what are they going to do next, right? Are they going to do the checkout, or are they going to, you know, do something else? So what is the label here? So the label in this particular case is the next sequence, right? So you can take event 2, 3, and 4, and then the label is going to be number 5, right? So you will always have a label in this case, because you can, like, as long as you have a next event, that is going to be your label. And some important aspects of this is if you want to do this problem, you need to be able to sort the events in order, like in the time that they actually happen, because otherwise you won't be able to sort them deterministically, and you need to be able to have a sequence, because in sequence problems the order matters. So make sure that you save timestamps on these. You also need to make sure that you can separate them between users, what users did what. It doesn't have to be personally identifiable, as long as it's like you can anonymize the data by hashing and so on, if you are afraid of data integrity. So make sure that you are able to separate users, because the events are important within the user but not across users, and timestamp everything. And that is also like a general rule with the data, like put a timestamp on everything. All right, so now we went through these 3 architectures. We're gonna have a look at the data, and this might become a bit technical and a bit heavy, but this is for understanding of how you should be saving the data. So if you're gonna apply machine learning, you cannot, for the most part, just use the data straight off, because the data is not gonna be saved in a format that is usable by a neural network. So you need to do a couple of tricks here and there, and feature scaling is one of them. So let's say that you have a data set that looks like this. You have age, name, device, timestamp, and then how much money they spent. And let's take a look at the age and the device columns here. So for the device columns, you can see that you have iPhone, Android, Chrome, and Edge. And this is not something that the neural network knows of, because this is text. And if you're going to do matrix multiplications, it needs to have a decimal number there. So what you will need to do instead is you need to discretely take all of these categories here and figure out how many of these do we have, and then you will do something called a one-hot encoding. So for example, for the first example here, you can see, is it an iPhone X? Is it Android? Is it Chrome? Or is it Edge? So you're going to have one new feature for all of these categories. And then you just put a 1 where it is true, right? So for the first example here, it is an iPhone X. Then you put a number 1 there. For the second one, it has an Android. So you put a number 1 there. And then you put 0 on everything else. So this kind of categorical data, it'll create a lot of features, which is going to mess up the data in terms of if you have too many categories, you're gonna have so many features, like thousands and thousands of features easily, right? So, and you cannot avoid this. Like sometimes you have to do this. So, but like this is just like to show you that categorical data is not as good as data, for example, like the age, where we instead can do something called the min-max scaling. And what a min-max scaling does, it just takes the data. You need to figure out the minimum value in your data set and the maximum value in your data set. And this x prime here, which is going to be our new prediction, it's just going to take the observed example. So for the first row, 20 here, it's going to take the minus the minimum value, which is also 20 in this case, because this is the lowest one. And it's going to take it over the maximum value observed, which is 52, minus the minimum value, which is 20. And that is going to give us 0 for Adam. It's going to give us 62.5 for Ada, and so on. So what this does is just scaling your data between 0 and 1. And this brings on the important requirement that you will need to be able to figure out the minimum and the maximum value for all your data, for your whole data set. And that you might not be able to do that all the time, but sometimes you can predict it, and it doesn't need to be 100%, but like the more closely to the maximum, the better. Sometimes you'll be able to take some of the features that you have and aggregate new data from it. Because the same thing goes with timestamp, that you cannot smack the timestamp right in as a feature into the neural network. You need to work around it a little bit so you get a decimal point showing that the muchness of something really means something, right? So if you take the timestamp column here, you can aggregate that out to at least 4 new features. So you can take, for example, the time of the day, which like this was in the morning, so it was like almost 50% through the day. And the same thing for this one, it was about like, it was in the morning, so it was only 35% through the day. And this was around lunch, so it was about 50% through the day. And this was like a little bit in the afternoon, so it was like 72% or 73% through the day. And you can do that for all the example, like time of day, and you could do the same thing like day of the year, which is like this was in the 1st of January 2018. So this was day of year 0. And day of month was also 0 because it was the 1st of January. And the day of week, I don't know what day of week it was. Maybe it was a Monday and then it'll be 0. Or maybe it was a Sunday and then it'll be, 6. So think about that. And that means that as you, it's what that's going to do with your data when you train it, it's going to show you that as we progress through the month and the day of month increases, that is going to mean something for the label that we picked later. And that is an important aspect. So think about how you would do this data aggregation. This can, also be done later when we train the data, which I don't suggest that you save the data like this necessarily. This is just, if you remember from the almost first slide, if you want to speed up. You can always figure this out and aggregate it when you're doing the training, but save the timestamp because this is what you're going to get from it. Some important aspects that is really important is like class imbalance. And a lot of people, they think like, yeah, we have so much data and so on. We're sitting on a gold mine here. But, not necessarily. Like if you're trying to do a hot dog, no hot dog classifier, is there a hot dog in the image or not? You need to have 50% of images with the hot dog, actually. If you only have like 1% of images that actually have a hot dog in it, how can you possibly do a training on that? The hot dog image is just gonna, it's gonna be crap because you don't have a good class balance between the examples. And the one with the least on it, like if you only have 2 images with hot dog, then those 2 images is gonna set the threshold of how much data you actually have. And the same thing goes for if you only have images of hot dogs and only like 2 images without hot dogs. That also means that you only have, 2 images to actually train on, because the lower bound is going to set how big your data set is trainable on. And this, I cannot emphasize this enough, right? So check your class balance to see, do we have 50-50 or do we have a good balance between the classes that we're trying to predict? And this is also why you need to think about what questions do you want to ask your neural network really early on. And of course, like data availability, like sure, you might have the database spread across, 100 different databases. That's not going to be possible, right? So make sure that you have the data available for training on. And as I said, like, do you know what questions you want to answer? And if you don't know what questions you're gonna be asking the neural network, how can you possibly select the label for the data set? And how can you possibly train anything on that? So, think about this. This is what you should be focusing on from day one. And categorical data creates a lot of features, as we saw. Is it possible that you can find other features that isn't categorical data, that is like a decimal number or something? That is way better to train on. Most of the time, you're gonna have some categorical data. You cannot get around it. Hopefully, it's just gonna be a few, but like not too many. But there are some tools that you can use. For example, dimensionality reduction to figure out which of these categorical features should we include. Maybe you can remove some of them. Like maybe you don't need to have the category of is it a Netscape Navigator? Maybe you can remove that feature because no one is using that anyway. So you need to sort and filter out stuff that is just creating noise in the data. And a really, really important thing also is the lack of transparency that you will get from some of these systems. So if you have a database with image recognition, for example, If you only train your image recognizer on white people, the model is definitely going to become racist because it won't recognize colored people and stuff. You might run into problems like that. So think about what kind of data you give it. I mean, the model doesn't think anything. It just does a statistical representation of the data. And if you only give it white people, it's gonna think that that is the definition of people. So think about that before you train it, so you don't run into stuff like that. And also, especially with images, you can most of the time do a lot of data synthesization. So, for example, you can create more data from the data that you already have, and you can introduce a little bit of noise, and it'll also become more robust to the real-world example. So I suggest you do this. Also, you can flip the image, and you can mirror it, rescale it a little bit, and mess with the hues and colors, and that way you'll get more data. If you have a class imbalance, which you're most likely going to have a little bit at least, most generally there's like a lot of techniques for this, but what you usually do is either you do upsamples. You upsample the data set, so you would take the lower class that you have few examples of, and then you would duplicate some of these examples. And you can do the opposite also. If you have much data but you have some class imbalance, maybe you can remove the majority class so they'll become more even. So you remove some data. And also, like, remember that if you're going to do training on this data, about 20% of the data you cannot train on because you need it for evaluation of the model. And this is a bit hand wavy as well, because you can get around some of this with some techniques where you reuse the data, but that has some trade-offs, which I'm not going to cover. Also, think about if you actually, are able to derive some of the metrics that you need for data normalization. You need the min value and you need the max value for all your features. Can you really get that? Sometimes if you have a lot of data, or the data is coming from a stream, maybe you're not able to get a min value or a max value because you haven't seen all the data yet. So think about that also, like in your domain of the problem that you're trying to solve, can you get a min and max value? Some of the important aspects when it comes to infrastructure is that you figure out where does the data live. Is it data at rest? Most of the time this is going to be the case. Like, is your data somewhat stable? Is it in a database somewhere? Hopefully one database, but most likely multiple databases. Then you can use Apache Spark, which is mostly Java world, also a bit hand wavy. There are other alternatives, of course. But in the wild, I see mostly people using Java for this. So you can use Apache Spark for this and do some kind of MapReduce job and merge them together. If the data is not at rest and it's coming from a stream, maybe you have so much data you cannot even save it because there is back pressure in the data. I suggest you take a look at Apache Flink, which is also mostly Java and Scala world. And then you also have to think about how you will find min and max values from the dataset, which I mentioned previously. And Apache Flink helps you out a little bit here with this min and max thing, so you don't have to know all these heavy algorithms necessarily by yourself. Some other aspect that you have to think about is how fast do you need to build new models. So do you continuously train the model, basically, as data comes in? Or do you do it once a month? Maybe you take a database dump and then you feature scale it and normalize that data set, and then you retrain it for a couple of days and then you deploy it. Or is it just a one-time thing? You have a data set. There is no more data coming in, then you train it. Like, where on this scale are you? But this is going to have trade-offs, how you would handle the data. Think about that. Continuously is way harder to solve than once a month or even once. If you have images, I suggest that you think about through your system that you have. Where do you have images in your data set? What do they do? Do they have labels? Do they have both negative and positive labels? Are they uniform? Meaning, do they have the same resolution? Are they of the same size? Do they have the same color scheme? File format, is it mixed with JPEGs and PNGs, etc.? can you make them more uniform in preparation? That is also really important. If you can do that while you're saving it instead of doing it afterwards, it's going to save you a lot of time. And this is the last slide of the presentation. This is just for some of the keywords that you commonly see. I just, took some of them while I was going along doing the slides. So this is mostly for non-developers. So if you hear someone talk about TensorFlow, that means the framework that you would usually build this kind of stuff in, that Google made. It's really common to use it. And Python is a programming language that you most commonly see within data science. And, machine learning is included in the data science field. The backpropagation I mentioned, and backpropagation is the activity of changing the weights in the model according to an observed example, the label, basically. And this is how the model learns. The gradient is also related to this, and the gradient means basically how big of a step towards the observed label do you take from, how much should the model change when it is correcting itself and learning. And the gradient descent is a specific algorithm for calculating this. And there are others for this. This is the most common, and there are a huge, maybe not huge, but there is a couple of implementations and improvements on the vanilla gradient descents. And the linear algebra is the field of the math that most of this stuff that I talked about covers, which is the most relevant mathematical field of machine learning. Some of these tasks includes matrix multiplications, which is the thing of machine learning. Basically, that is what you do most of the time, multiplying matrices on the GPU. And you have them in different sizes, and there are some rules of how you can multiply them and how the size of the output matrix changes. And this belongs to linear algebra. And what you can do with matrices are multiplication, addition, subtraction, but you can't do division with the matrices. Also, a big difference is how the order by which you multiply them matters, but that's a side note. I briefly mentioned activation function, and the activation functions are special operations that you put in between the layers. So, like if you're multiplying two matrices together, what you do basically for each layer is you have a matrix, and then you have some other matrix, you multiply them together, you add something called a bias, and then you pass the whole output matrix that you get from that through an activation functions. And you need to have activation functions enabled to solve non-linearity problems. And some of the implementations of these are most commonly ReLU, Sigmoid, and Softmax. And they have different behaviors, and you use them for different stuff. Data normalization is, I also mentioned, is the purpose of this presentation is the same as feature scaling, as I presented. And also really important is overfitting, which means that if you have a model and you have trained it too much on the training data, you have passed through the data set more than once, and you're training it and training it and training it on the same data, you have too little data. What's going to happen is that it's going to do something called overfitting, where it's performing really good on the training data because it had, fitted everything in exactly from the training data. But when you give it some other data from the real world, it doesn't know anything because it haven't, generalized the problem in a good way. So it can only do it for data that it has seen and not for data that it hasn't seen. So that is what overfitting means. And that is all for this presentation. I hope you have gained some insights and inspiration of how you should be working with your data for the system that you're building. And if you have any questions, you can contact me on LinkedIn or leave a comment in the video section, and I'll try to answer it when I have time. All right, so thank you for watching, and I will see you. Bye-bye.